Next speaker will be Tobias from the Brenner Basistunnel, and we will move into a totally other subject, namely the tunnel infrastructure and the planning, construction, and operation that we can learn from one of the two large infrastructure projects in the GunMed corridor. So Tobias, can you hear us?
Hello. Can you hear me?
Yes, very good. Thank you.
Okay, thank you very much. So my name is Tobias from the Brenner Basistunnel in Innsbruck, and I will give a short overview of the best practice case sustainable planning, construction, and operation of tunnel infrastructure. To develop and promote green transport operation, we have heard today of a wide variety of innovative measures which are now included in the Swift Green Toolbox. But also measures for sustainable infrastructure is a prerequisite for green transport, as we just heard from Birgit. The following best practice case comprises measures of green innovations. The aim was to concentrate on today implementable practice cases and on the implementation in the BBT project. Through this combination, we received direct feedback and additional knowledge. And both we want to share within our measures in the Swift Green Toolbox. The Brenner Basistunnel, as we saw before, is part of the Scandinavian Mediterranean corridor between Munich and Verona. The removal of this bottleneck is crucial for the realization of the corridor and consequently to ensure the modal shift from road to rail. It is also crucial for the future of the ecologically sensitive Alpine region. Thanks to the almost horizontal tunnel, train traffic will no longer have to contend with the steep up and downhill slopes on the old 20-kilometer longer Brenner railway line. These two obvious and directly comprehensive improvements illustrate already important planning aspects of sustainable infrastructure. These aspects result from several years of planning process and optimization runs of the design project. But especially for the planning of infrastructure, a detailed evaluation of the sustainability of different alternatives is highly complex. For this purpose, life cycle assessments should be used to promote the green infrastructure solution. During the planning process of infrastructure, greening objectives are very important, but strongly project dependent and hence not easy transferable. So first, we concentrate us on main tunnel infrastructure subjects to receive the following solid transferable measures. The BBT measures shown here are identified measures from our best practice guide, comprising examples of greening innovations implemented at the infrastructure planning of the BBT. They are chosen carefully to receive solid and effective measures to guarantee a sufficient transferability to other tunnel infrastructure projects. For sake of simplicity, I will now consider only 7 of these measures and concentrate them to 3 tunnel-related subjects. First, the recycling of tunnel spoil. Second, the concrete with minimized environmental impact. And third, the geothermal energy exploitation in tunnels. So we start with the recycling of tunnel spoil as an example, where you see here a tiny portion of the BBT tunnel spoil. In the past few years, several large tunnel projects have been completed or are under construction in the Alps. Generally, the tunnel spoil material is categorized as waste disposal. And according to Entacher, it represents the largest waste stream by quantity in Austria. The recycling of tunnel spoil at the BBT, shown here, the Brenner Basistunnel with a total length of 64 kilometers have 15.5 million cubic meters of spoil, which will be excavated. This amount of spoil is equal to the volume of 8.5 times the Cheops pyramid. The primary objective is the recycling of the aggregate part of the spoil as filer, drainage gravel, solid and loose foundation layers, and as aggregate for concrete. The main interest in recycling spoil is, of course, its use as an aggregate for concrete production. The result of this implementation implemented measures you can see below. It's a process plan at the BBT site in Wolf, Austria. It was optimized during the year 2014, and since November 2014, the aggregates used in producing shotcrete and construction concrete have been 100% sourced from the processed tunnel spoil. Due to the complex dependency of these measures, evaluation by life cycle assessments are realized to confirm and estimate the greening effects. These life cycle assessments give detailed insight about dependency and environmental impact of infrastructure construction on the one hand, and quantify the reduction of the environmental pollution on the other hand. As the main result of this study, it can be said that the use of the tunnel spoil and the types of shotcrete used in the access tunnel involved spare a considerable amount of mineral resources. The use of tunnel spoil also reduces the environmental pollution. So, not at the same level as for the mineral resources, but in a way. Additional, the transport is reduced and the area of landfills is decreased. So this is a summing up of this life cycle assessment. I skip to the second subject. It's concrete and shotcrete as a key material in tunnel construction. Generally, concrete delivers carbon dioxide emissions between 100 and 200 grams of carbon dioxide per kilo of concrete, as well as some energy requirements. However, due to the large volume of concrete required in infrastructure projects, its use imposes considerable strains on the environment. According to the World Resource Institute, the worldwide cement industry accounts for about 5% of the global carbon dioxide emissions. You can see an example of an inner concrete tunnel lining at the BBT. The application of concrete and shotcrete are areas where beneficial improvements concerning the sustainability could be made. Within Swiftly Green, we did several studies about the material technology optimization and the eco-balance of the different concrete recipe. The main result of this study are improvements to the ecology and durability and the sintering potential. So we achieved reduction of around 30% carbon dioxide equivalents and meet the requirements on the site. Also, we reached a considerable boost to the material's sintering potential and an increase of the resistance against sulfur attacks. This is very important for the durability and the availability of the tunnel. The latter two aspects have both a major impact on the future maintenance and on the overall infrastructure availability. Next, we skip to the geothermal energy exploitation and begin with the thermal use of tunnel drainage water for heating purpose. The thermal use of drainage water is an economically effective way to providing energy to buildings near the underground infrastructures. It is already a standard technique and it is applied in many alpine tunnels. Especially for deep tunnels, the tunnel water reaches high temperatures. Due to the long distance, these high temperatures drop to 24 to 28 degrees Celsius at the tunnel portals at the BBT. According to the BBT studies within Swiftly Green, still an exploitable power of 15 to 40 megawatts can be reached. An innovation of installing a cold district heating network nearby the tunnel portal instead of using heat pumps would decrease heat losses and increase the versatility of the system. The second possibility for the geothermal energy exploitation is the tunnel lining energy exploitation as a closed-loop system. Here you see an example for a segmental lining. This environmentally friendly geothermal energy exploitation involves the use of a closed-looping piping system. In this closed system, a fluid circulates in a pipeline in the deep ground, extracting the heat. As you can see here, an example. An alternative is the point B, where pipes can be installed in situ between the preliminary lining and the final lining. For heating purpose, both systems will decrease the temperature in the tunnel and hence will decrease also ventilation needs for the tunnel. These studies show exploitation of 500 watts per meter of tunnel. Also here, the temperature is too low for direct usage in an existing heat system without a heat pump. A cold, strict heating network nearby the tunnel portal would improve the efficiency of the heating system. So to conclude this short overview of the sustainable infrastructure measures which were included in the Swiftly Green toolbox. The investigated greening measures from BBT show high potential to increase the sustainability of the infrastructure itself. In future, further effort is needed to collect more best practice cases and to promote these best measures until realization. Thank you very much.